Okay, question number 6. The diagram shows an arrangement that used to determine the magnetic flux density of the poles of a magnet. Okay, so the magnet is placed on a sensitive top pan balance. So a current carrying wire is placed at the right angles to the magnetic field, so between the poles of the magnet. So the force experienced by the current carrying is equal but opposite to the force by the magnet. So the magnet is being pushed down when the wire experiences an upward force. Okay, so now our arrangement here is to create a force that it will uplift, okay, so that there will be a downward force, which is our third law of Newton. Okay, action and reaction force. Okay, where there is an action force, there must be a reaction force. Okay, so the length of the wire in the magnetic field is 5 cm. Now the balance reading is 102 gram when there is no current in the wire. So the balance reading increases to 103.14 gram when the current in the wire is 8.2 ampere. Show that the force experienced is equal to 1.1 times 10 to the power negative 2 Newton, and calculate the magnetic flux density of the magnetic field between the poles of the magnet. Okay, so I need to calculate what is the force to prove that it's 1.1 times 10 to the power negative 2. So it's very simple. Okay, according to the Newton's law, the third law of Newton's, the force that experiences is actually the gravitational force. Okay, now there is a change in the balance, so that I use this minus 102. Okay, now this is gram, remember, times negative 3 times 9.81. Okay, so check your calculator, you will get it as 1.1 times 10 to the power negative 2 Newton. So it's proof. Okay, now B is find the magnetic field. Okay, so now since I have the force over here, so according to the third law of Newton's, my magnetic field force will be equal to the gravitational force. So 1.1 times 10 to the power negative 2 will be equal to BIL. Okay, so B is what you have to find. Okay, now the current here is 8.2. Okay, so 8.2 times, now the length is 5.0 times 10 to the power negative 2. Okay, so my magnetic field here will be 0.0268. Okay, so it will be around 0.027 Tesla.